problem number 7 says, I want to prove which of these series converges absolutely, conditionally, or just diverges. So looking at number 1 in this case, I have negative 1 to the n cosine 1 over n to the 5. So what I'm going to do in this case is I'm going to apply alternating series formula and see if I can figure out if it converges or not. So according to this, the first criteria you need to satisfy for alternating series test is you need to take the limit of b sub n and it has to be 0. So my b sub n in this case is cosine of 1 over n to the 5. So cosine 1 over n to the 5. So cosine of 1 over n to the 5, if I take the limit of that as n goes to infinity, I end up with cosine of 0. Cosine of 0 is equal to 1. So it already fails the first criteria for alternating series test. Because 1 is not equal to 0, not only does it fail it, it automatically diverges by test for divergence. So if it fails that first criteria for alternating series test, it's automatically divergent. So I'm just going to go ahead and write D next to 1. Number 2 is cosine of n pi over n squared. Again, it's an alternating series. Cosine of n pi is an alternating term. So I can still apply alternating series formula to it. So again, I need to satisfy the criteria. So the first one is that limit as n approaches infinity of 1 over n squared should be 0, which it is. N squared is growing faster than 1, so therefore the bottom will grow faster than the top, which means that it will go to 0. So the next term, that's the first criteria satisfied. The next criteria you have to satisfy is that b sub n is decreasing over time. The way you prove that, take the derivative of b sub n and see if it comes out negative. So if I take the derivative of 1 over n squared, I end up getting negative 2 over n cubed. That term is negative, so therefore it should be decreasing over time. What this means is that if I take the derivative and it's negative, that means that the term has a negative slope. If it has a negative slope, it should be decreasing over time. So it satisfies both criteria. What that means is that this series converges conditionally by alternating series test. So we do know it at least converges conditionally. But the question still remains, does it converge absolutely? So to prove absolute convergence, I need to take the absolute value of my series. Taking the absolute value of my series yields sum from n equals 5 to infinity of 1 over n squared. So by taking the absolute value of cosine of n pi, it basically just becomes 1. So I end up with 1 over n squared. By ending up with 1 over n squared, I need to find some kind of way to prove convergence or divergence. Well, I know 1 over n squared I can use p series for. So 2 is greater than 1, so therefore this should be convergent by p series. If this is convergent, that means that it's absolutely convergent. And the reason is again, I took the absolute value of my original series, I ended up with that, and it is still convergent. Because it's still convergent, the whole series is absolutely convergent. So I'm going to write A next to that. Number 3. Number 3, I actually have the ability to split this into 2 different series, which is good because I really don't know what this is going to do over time. So what I'm going to do is I'm going to split this into 2 different series and see if I can figure out what's going on. Infinity. I end up with 3 over n minus sum from n equals 8 to infinity of negative 1 to the n over n. Now I know that negative 1 to the n over n should be conditionally convergent. And that's again just by proving it using alternating series test. But I have a problem. I have 3 over n. 3 over n is definitely divergent by p series. So if I have a divergent series minus a convergent series, the overall series is divergent. So convergence is always eliminated by divergence. So unless these were both convergent, there's no way this whole thing could be convergent. So number 3 is divergent. And that's because 3 over n is divergent series. Now, I have number 4. Number 4 is, again, it's an alternating series, so I can apply alternating series test to it. So, take the limit as n goes to infinity. I end up with 1 over n to the 1/2, natural log of n, as my b sub n. If I take the limit of that as n goes to infinity, that definitely goes to 0. So, that's one criteria satisfied. The next criteria, I have to see if it's decreasing over time. Now the derivative of n to the 1/2 times natural log of n is kind of a hard one to take, but it does in fact decrease over time. So both criteria are satisfied, which means that this series should be conditionally convergent. However, I still need to prove if it's going to be absolutely convergent or not. So by taking the absolute value of this, I end up with n equals 5 to infinity of 1 over n to the 1/2 natural log of n. Now, n is the dominant term on the bottom here. I know that n to any power will always grow faster than natural log of n. So what I'm really interested in is what this n is going to do. Now, there is a rule that says that as long as n, if the power of n, when you have something like that, is greater than 1, there is a chance it could be convergent. It all depends on the power of your natural log as well. So if n is greater or equal to 1 and p is greater than 1, that series will be convergent. But if n to a 1/2 is on the bottom, that means that it's divergent. And the reason is because n to the 1/2 is overshadowing natural log of n. N to the 1/2 is divergent by p series. So therefore, this overall series is divergent when I take the absolute value of it. However, it started with an alternating term, which means that it should only be conditionally convergent. So when I took the absolute value, it didn't converge anymore, but it still converged when I had that alternating term in there. So this term, I'm going to mark it as C. So my first series was divergent, my second one was absolutely convergent, my third one was divergent, and my fourth one was conditionally convergent. Because of that, my answer is C.
The Teaching Center, UF's Learning Resource Center.